All right, let's get right into it. Today, we're going to break down the design of a system that, is absolutely crucial for keeping the internet stable and fair for everyone. We're talking about a distributed rate limiter.
Yeah, I'm willing to bet you've seen this one before. That error message? It's pretty much the most common sign that you've just run into a rate limiter. It's the system's way of, well, politely saying, hey, maybe slow down a bit.
So what is a rate limiter exactly? Well, the easiest way to think about it is like a traffic controller, but for an API. Its whole job is to control how many requests any one client can make in a certain amount of time. And trust me, it's not just there to be annoying. It's actually super important for preventing abuse, stopping servers from getting totally overwhelmed, and just, making sure everyone gets fair access.
Okay, so if we're going to build one of these, we need a blueprint, right? And it all starts with two really fundamental questions that are going to shape our entire design.
So first up, where does this traffic cop actually stand? You've got a few options, really. But for our design, we're putting it right at the API gateway. And this is a pretty brilliant spot for it, because the gateway is the single entry point for all incoming traffic. That gives us this nice, centralized control without making every single request take an extra network trip.
Okay, second decision. Who are we actually limiting? I mean, we need a way to identify who's making the request. We could do it by user ID for people who are logged in, or maybe by IP address for anonymous traffic, or if it's for other developers, an API key. And honestly, in the real world, big systems don't just pick one. They usually layer all of these rules together to create a much smarter and fairer system.
All right, our blueprint is taking shape. Now we get to the really interesting part, building the brain of the system. We need to pick an algorithm that's actually going to make the call on every single request, allow or deny.
And this is where it gets really interesting, because there's no single best algorithm here. It's all about trade-offs. You look at something like the fixed window counter, it's super simple and doesn't use much memory, but it has this weird quirk where you can get a burst of double the requests right at the edge of the time window. Then you have the sliding window log, which is perfectly accurate, but man, it eats up a ton of memory. The sliding window counter is a cool middle ground, a hybrid, but it's a bit more complex to build. And that brings us to our fourth option, the token bucket.
So for our system, we're going to go with the token bucket algorithm. And why is that? Well, it's because it handles the unpredictable nature of how people use APIs so well. Think about it. Real users don't send requests at a perfect steady pace, right? They're quiet for a bit, then they do a bunch of things at once. The token bucket's design lets you save up tokens for those bursts, which makes it a fantastic fit. It's that kind of flexibility that makes it a top choice for companies like Stripe.
Okay, so we've picked our algorithm. Awesome. But because we're building a distributed system, we've just created a brand new classic problem for ourselves. If we have a bunch of servers in our API gateway, how do we make sure they all know how many tokens one single user has left?
Seriously, think about it for a second. What if your first request hits server A and your next one hits server B? How in the world does server B know that you already spent a token over on server A? If every server just keeps its own private count, well then our rate limiter is completely useless. We need some kind of shared brain.
And that shared brain is Redis. For this job, it's perfect. It's a ridiculously fast, in-memory data store that all of our gateway servers can talk to. So Redis becomes our one single source of truth for every user's token count. This way, we can make sure that every request, no matter which server it happens to hit, is looking at the exact same up-to-date information. But wait, there's a trap, a really subtle one. And this is such a great example of a classic problem in distributed systems. Just follow this sequence. 2 requests for the same user arrive at the exact same time. Both servers read from Redis. Both see, hey, there's 1 token left. So both of them say, yep, you're good to go, and let the request through. Whoops, we just let 2 requests through on a single token. That, my friends, is a race condition. So the big question is, how do we fix this? How do we stop 2 different requests from spending the very same token at the very same time?
The fix is a really powerful concept called atomicity. Think of it like a bank transaction. You can't just withdraw the money without also updating the balance. It has to happen all at once or not at all. We need to do the same thing here. Bundle the read, calculate, update logic into one single indivisible operation. We can't have separate read and write steps anymore. And in Redis, the way we do this is with a Lua script. It basically tells the database, hey, run this entire block of code and don't let anything else interrupt you while you do it. And just like that, problem solved.
Okay, so our logic is sound now. It's correct. But now we have to face a completely different kind of challenge: scale. can this system actually handle the massive traffic of a major platform?
And we're not talking about a few thousand requests here. We're designing for an absolute fire hose of traffic, 1 million requests every single second. And a single Redis server, even as fast as it is going to turn into a bottleneck real fast. There's just no way it can handle that kind of load on its own.
So that leads us right into our next big challenge. If one server isn't going to cut it, how do you scale a database to handle that kind of insane traffic?
Well, the answer is a technique called sharding. Basically, we split our data across a whole bunch of Redis servers. But, and this is a big but, we can't just do it randomly. If we did that, a user's data might be on server A, but the next request goes looking for it on server B, and chaos. To solve this, we use something called consistent hashing. It's this really clever algorithm that guarantees that all the data for one specific key, like a user ID, will always go to the exact same server, the exact same shard. And that is absolutely critical to make sure our rate limiter actually works.
Okay, our system is scalable, it's correct, but we're not done. We have to design for failure. What happens when the inevitable happens? What do we do when one of our Redis shards just goes down?
And this brings us to a really critical decision. We have two basic choices. Do we fail open, meaning we just let all the traffic through? The risk there is that we get a massive flood that could crash our entire backend. Or do we fail closed and just block requests for the users on that broken shard, causing a small, temporary outage for them? There's no easy answer here. It's all about picking which risk you'd rather take.
For a system like this, we're going to choose to fail closed. Why? Because a brief outage for a small number of users is way, way better than a catastrophic failure of the entire system. But honestly, the best strategy isn't just deciding how to fail, it's preventing the failure in the first place. So we'd use something like master replica replication. That way, if a master Redis server goes down, one of its copies, a replica, can get promoted and take its place almost instantly. That minimizes the downtime dramatically.
And all of this kind of brings us to a final, bigger thought. We've just walked through designing this complex system with algorithms and databases and scaling strategies, all just to protect our services. And it really makes you think, for a system to be truly reliable, does it first have to learn how to say no? That's really the whole point, isn't it? It's the reason you see that too many requests error, and it's the invisible guardian that keeps the services you use every day up and running.